Okay, welcome to this session. In this session, we'll focus on power system component modeling for a power flow analysis. So, mainly we'll focus on a generator modeling as well as a transformer modeling for this session. So, when we are talking about power system component modeling, we will represent the power system component by equivalent electrical parameters. So, to carry out a load flow analysis or a power flow analysis, those components like a generator and a transformer, transmission line should be represented by equivalent impedance or voltage source so that we can analyze by applying a circuit theorem. So based on the role in a power system, we can classify a generator as a PV generator where active power and the voltage will be specified, whereas reactive power can be calculated by using a power mix engine iterative method. In addition to that, we will have a slack bus. So what we call on a slack bus, we have a slack generator. So the selection of a slack generator is based on the capacity of the generator. So a slack generator is selected by taking the generator that has high capacity within existing distribution system. So a slack bus is used as a reference so that the reference voltage and the reference voltage angle will be specified for the slack bus. But the active and the reactive power is calculated based on the power mismatch. In addition to that, in a power system, we'll have a PQ bus where active and reactive load is already determined, so we calculate a voltage and a voltage angle. The calculation of this voltage angle is done by using the iterative method. Maybe we can apply a Gauss-Seidel interruption and other iterative methods to determine those parameters. So a slack bus is also called a reference bus. As I tried to say earlier, it is called a reference bus because for a special generators which is used as a slack bus, will provide a reference voltage and voltage so that the other voltage will be calculated based on this reference. So when we come to a slack bus, it has voltage and voltage angle as a specified parameter. But for the case of a PV bus, we will have active power and voltage angle and other parameter like a bus voltage as well as the reactive power will be calculated based on the power side. So proceeding to the generator representation, when we see a generator, for a simplicity, generator is represented by using internal voltage source with a series impedance. So the generator will have internal impedance, which is RA plus JXA, so that it can be connected to infinite bus or a load. So the terminal point connection voltage is specified at B terminal. So the load can be connected to the generator at a different power factor. For a powerful analysis, the simplified representation of a generator look like this. So we'll have a generator, we have internal voltage, this is the internal reactance of a generator, and this is a terminal voltage that will be supplied to the load. Based on the load power factor, based on the load power factor which is supplied by a generator can operate in a unity power factor, lagging power factor, or leading power factor. For example, if it's working at unity power factor, the armature current and the terminal voltage will be in phase. Here, it is armature current, and up to this point is terminal voltage. So in that case, we can develop a power curve by using this relation. Since armature voltage and terminal voltage in phase, the power drop due to internal resistance is in parallel with a terminal voltage. So it is like additive on terminal voltage, but the voltage drop due to a reactance is perpendicular to a current. So we can draw it like this, and we can obtain the internal voltage. So the internal voltage should supply the terminal voltage plus the voltage drop due to active and reactive part of impedance. And we can calculate the magnitude of voltage drop due to impedance by using this relation. But when we see a load which has a power factor of lagging as theta, the power curve equation will look like this. So if the load is at a lagging power factor of theta, and this is a voltage at a terminal point, and this is armature current, so there is angle difference between terminal voltage and armature current, what we call power factor angle. In the same principle, the voltage drop for a lagging power factor due to a resistance is in parallel with a current. So it's have the same direction as the current. So this is the voltage drop due to resistance. Again, the voltage drop due to a reactance is perpendicular to the current. So we can have internal voltage which should has to be equal with a terminal voltage plus this drop. And again we can calculate the magnitude of internal drop when the generator is operating at lagging power factor, which is mostly rare, but it can be possible to have a leading power factor if our generator is connected to a load which has a leading power factor, and this is our terminal voltage and this is our armature current, because there is leading power factor of theta at that time. So like previously theorems, for a leading power factor also, the voltage drop due to resistance is in parallel with a current. So this is the voltage drop due to the resistance part of the impedance, whereas the voltage drop due to reactance is perpendicular to the current. And this is the internal voltage. This internal voltage should give the sum up of these voltage drop plus terminal voltage. Again, we can calculate the magnitude of internal voltage drop for a power factor. So considering what three scenarios, again ignoring one reality that when we see the internal impedance of a generator, the magnitude of internal resistance is very small compared to the internal reactance. That's why we keep only here the internal reactance. So considering that, if we draw a power curve, a internal voltage relation, terminal voltage and the power factor for a three cases on the same axis, we'll have this. For example, let us consider the lagging power factor, where the current lags the voltage magnitude at some point. For example, if the unity power factor is there, this armature current IA2 and the terminal voltage are also the same direction with the armature current. So by ignoring the resistance, the magnitude of a voltage drop due to reactance is perpendicular to the current, and we will have this E3 internal voltage. E3 internal voltage, whereas the angle difference between V and E is called a power angle, and we have this magnitude of power angle. In addition to that, if the load is connected to the lagging power factor, so our terminal voltage is similar. We have this terminal voltage, and our current is this IA1. So since the current is lagging the voltage, and we have only reactance by ignoring the resistance, the voltage drop due to the reactance when lagging power factor is following those. This internal impedance of a generator is perpendicular to this current. So this perpendicular current to the IA1. So for that also we have this magnitude of internal voltage. So we have internal voltage of E1 for lagging power factor, E2 for unity power factor, and for E3 also, like, we have terminal voltage. This IA3, which is leading power factor current. So in the same principle, since current is here, the terminal voltage is here, the voltage drop due to this current is perpendicular to this current. So if we draw a perpendicular line to this circuit, we have this, and at this point we have E3. Whatever the scenario is that the magnitude of internal voltage is dependent upon the types of a load connected to the terminal voltage. So this relation can be easily obtained by using, for example, if we consider the vertical component of this voltage, CD can be obtained as the E1 sine of theta 1, because this theta 1 is E1. By using sine of this, we can have this opposite magnitude. So CD is equal to E1 sine of sigma 1, when sigma 1 is a voltage angle, not power angle, between E1 and the B1, is equal to XS IA1 cos theta. So this is a cos theta 1, this XS I1, and the magnitude of this angle and the magnitude of a power factor theta 1 is equal, because these diagrams are parallel, this dot and this terminal voltage line is parallel. So this is IA1, and this is the perpendicular angle to the IA1. So if you use that relation, this voltage, this angle, theta 1, and this theta 1 as equal. You can refer the relationship. In addition to that, to get a power equation for a generator, the power equation for a generator is obtained by using 3 times V terminal times IA conjugate. When we say the conjugate means, you know what's conjugate. Conjugate is obtained for a complex number by changing the sign of the imaginary component part. Or you can see that what's conjugate for a complex number, or how we can get a conjugate for a complex number which is specified as magnitude as some angle. So 3 is due to 3-phase, voltage is terminal, is I conjugate. So the terminal volt current for the generator is represented by this equation, because it's a very simple equation. Here we have terminal voltage at angle 0. Here we have E internal at angle sigma. So the difference between this voltage divided by impedance is a current, is very simple equation. You can get this. So by considering this equation, so ZS is like the complex representation of this impedance. So we can have this relation. This is IA. So by taking the conjugate of this number, we can have a final equation for this representation. So the general power output of the generator is represented by 3 times E is internal voltage, V, Z is the impedance, at angle of, this is angle of the impedance, this angle of internal angle of the synchronous generator, and this is B terminal, and this is angle of impedance. So you can obtain that. In addition to that, we can decompose this equation into active and reactive. For decomposition, we'll use cos part will be the active power and sine will be the reactive power. But if we ignore the RA, the angle sigma will be 90 degree. So for a 90 degree, you can apply a double angle formula and finally you will arrive on this equation for active power and this equation for reactive power. But the magnitude of the maximum power of the mediators depend upon the internal voltage, terminal voltage, and time impedance. So to apply that, what is a double angle formula? Remember to this. For if two angles A and B, the sine of A plus B is obtained by using this equation. So you can apply this for a cos. If cos A plus B is given, we can apply this for a double angle formula. For sine also we can apply if there is difference between angles. So by applying that, we will obtain a final maximum output from a generator by this equation. 3 times E times V times XS. But one thing is you have to remember is that since the generator is used to supply a varying load under a power flow condition, the magnitude of output power will be specified or changed by changing the magnitude of sine sigma. When this sigma is used to represent a power angle, the angle difference between terminal voltage and internal generator voltage. So after obtaining this final equation, to apply the simple circuit theorem for a power flow analysis, we'll apply the equivalent representations Norton independent equivalent circuit to use this equivalent representation for a power system. So if we have a Thevenin circuit, which is we have input impedance, we have input source, and there is a load. So we can convert that to a Norton circuit by using a current source in parallel to Norton resistance and connected to the load. So to obtain that, what will do is that the magnitude of a Norton current is obtained by dividing V Thevenin by R Thevenin. And the R Norton is actually the R Thevenin placed in parallel current source. So Thevenin theorem and the Norton theorem are method used to simplify a complex electrical network in equivalent circuit containing only voltages, current source, and impedance resistance. So remember this circuit for a later use, because when we come to the formulation of the powerful equation, we will use a Thevenin representation for a generator to equate the current input to the bus and out, so that we can make a KCL as some bus, and we will derive a voltage and a current relationship. So let us see one simple example on generator representation power output calculation. For example, consider a series phase Y connected synchronous generator is connected to infinite bus. This is a three-phase generator is connected to a single bus. So this internal voltage is there, internal impedance is there, so infinite bus is there. So the generator terminal voltage V terminal is 6.3 kV line to line, and the internal generated voltage is 7.2. So the terminal voltage is 6.6 and internal generated voltage is 7. So there are about 0.6 internal voltage drop. The synchronous reactance per phase is 5. We ignore the resistance, and the synchronous impedance is 5 ohm. While the armature resistance is neglected, we neglect armature resistance, the generator operates a power angle of 25 power angle is sigma. Using a power angle equation for the synchronous data, determine the phase value of terminal voltage and internal generator, the armature current, three-phase active power output, three-phase reactive power output, maximum power that can be transferred from this generator. So it's very simple for internal voltage, external voltage of that. The armature current is obtained by using this equation. So internal voltage is 7.7, terminal voltage is 6.6, ZS is already given 5, and angle is 90. But this is line to line, and this is also line to line. We have to calculate a line to neutral to calculate for a current so that we can obtain the magnitude of current. So if we take terminal phase voltage, we'll have this magnitude, which is line to ground, by dividing by radical 3, we can obtain that voltage because we have to convert that to line to line by dividing by root 3. So in the same way for internal voltage also we have to calculate the line to go neutral. So the magnitude of Z is given, this angle is 90. So sigma is given as 25. We can calculate the magnitude of internal voltage. So for a given magnitude of internal voltage and internal reactance, magnitude of sigma is given, we can calculate the amount of power output for three-phase reactive power, so we can use this equation to determine the maximum voltage can be calculated. So this is how we can obtain the parameter required for that. So in addition to a generator representation, so for case of generator, we have seen that Norton equivalent circuit is very important. Once we get internal voltage and internal reactance, we can use a Norton circuit equivalent to model that in a power flow analysis. But when you come to a transformer, so transformers are again the second component that has to be modeled in power flow analysis. So for that, an ideal transformer would have winding with zero resistance and lossless infinite permeability. So this is the equivalent representation of a transformer. In transformer, we have a primary voltage, primary side winding impedance. We have a core for a transformer, and so this winding term, and this is the total impedance of the transformer. This is a load voltage. So by using this equivalent representation, finally we can reach to a simple circuit which can be modeled and used for a power flow analysis. So mathematical framework used to calculate and simplify this equivalent circuit relies heavily on a turn ratio. So for example, what we call a turn ratio is the magnitude of E1 to E2 is equal to the magnitude of E2 to E2 prime. So this the magnitude of a voltage, the magnitude of current, and this is the magnitude of the current secondary. This is referred current secondary to the primary side. So by simply applying this relation, and this is equal to N1 by N2. This is a simple transformer equation. So transformer has these components: primary winding, core, then secondary winding, and this is the transformer separation. So we can apply this circuit. So for example, if we see E2 is equal to B2 plus Z2 I2. This E2 is as a magnitude of a voltage which will be dissipated on winding component, and then some amount of voltage will be supplied to a load. So we can have this relation for E2. E2 is equal to I2 times Z2 plus V2. In addition, V2 prime, what we call V2 prime, is A times V2. If this V2, the referred magnitude of V2 is obtained by using A times V2 when A is a term ratio. A is a term ratio. So again, the magnitude of a referred current from secondary to a primary can be obtained by using this relation. This E2, then when it's referred to the primary side, it has a magnitude of I2 prime refer. And this relation is obtained as I primary refer is equal to I2 over A. So if you want to refer the impedance, we have a referred value voltage from secondary to primary, which is A times B2. We have a referred current from secondary to a primary, which is equal to A2 over A. So to get a referred impedance, we have to define a referred voltage by a referred current. So this becomes this magnitude. So by applying this, if we divide this relation A, if we divide AB2 by I over A2, we will get A squared times R2. So to refer the impedance from the secondary to the primary, we will multiply it with square of a terminal ratio. So to divide, to refer a voltage, we will multiply with a terminal ratio. To refer a current, we divide with a terminal ratio, whereas to refer the impedance, we will multiply it with a terminal ratio, where A is the ratio of N1 to N2. If the ratio of N1 to N2 is A, so impedance will be obtained by using N1 over N2 squared times the impedance in the secondary side. The same relation can be used to refer that to the primary, from primary to secondary. So if you see that, if you see this, the first circuit here, in this circuit, we have primary winding impedance, core impedance, and then voltage E1, I2 referred, E2, secondary winding impedance in this terminal load. So if we want to refer those parameters to this primary side, we have to multiply this impedance with a square of transformation ratio, and this voltage with square of transformation ratio, and this current divided by transformation ratio. So finally we'll have this circuit. So here we have V1 for primary impedance is as it is, core impedance is also as it is. So now we'll convert a secondary winding impedance to the primary side impedance by multiplying by this equation. You see this underlined equation is used as a transformation ratio. So we'll have referred secondary winding, which is Z2 prime here. So the magnitude of impedance is multiplied by transformation ratio square, whereas the magnitude of the current is divided by transformation ratio square. And the voltage of the terminals is also multiplied with a transformation ratio. So this is a simple circuit that can be used to represent a transformer which is referred to the primary. So this is a simple equation. One, remember a transformation ratio, which is N1 over N2. Then remember the transformer ratio relation with voltage and the current. Then write a simple equation, V2, E2 is equal to V2 plus Z2 I2. But remember, when we refer a voltage, how we can refer? When we refer a current, how we can refer? The impedance obtained by voltage over I. So we can simply obtain this relation. So finally, we'll have this equivalent circuit representation. Finally, what we do? We can move these parts to this or this part to this so that we have equivalent impedance. So the primary winding is there, the secondary winding is referred by multiplying with a square of the transformation ratio. So this current is obtained by dividing the current with the transformation ratio. This voltage is the terminal voltage, which is multiplied by the transformation ratio. So we can combine this and obtain Z equivalent. We can reduce the circuit. So finally, if we have this terminal voltage, the magnitude of core reactance is very huge compared to the winding resistance. So we can ignore this because this is a very huge resistance. There will be no current through this. We can further reduce the equivalent circuit to this equation. So we will have this input voltage primary. So this is the equivalent voltage which is obtained the primary winding plus a secondary winding resistance referred to the primary. So this is a voltage which is terminal voltage multiplied by the transformation ratio. So this is a simple circuit for a transformer. So we have this simple circuit value, this input impedance, then load, this ground. So we can obtain these values. So these components of the transformer is obtained from open circuit test and short circuit test to determine a core iron loss, to determine no load current, to determine a magnetized current, and as well as magnetizing reactance and the core impedance, we will perform open circuit test. What we'll do in open circuit test? We'll keep the high side of the transformer open, but we connect the low side of the transformer to the source, and we'll increase the magnitude of voltage up to a rated voltage, so that we'll measure a magnitude of a current, the magnitude of a power, so the voltage will reach the rated voltage. So we'll obtain this. One thing is clear now. We'll not have a current flowing to the high side because it's open. All currents that come from this is obtained and pass through the core winding, core resistance and the reactance. Because we have current here it's open, there is no current, all current will go through the core resistance and the reactance. So we have here a meter which is active power measurement, current, and so on. But for the case of short circuit, the voltage will be applied to a high voltage side. So all components, current, voltage, and the wattmeter will be used, whereas the low side will be short circuit. So for this case, for open circuit, we'll apply a rated voltage and calculate rated voltage and measure the current, and already rated voltage is there. From that, we will calculate a core component. But for a short circuit, we'll short the high voltage side, but we'll make the voltage at 0 level. So slowly increase until the current measured by the primary side reaches the rated magnetic. So maybe this part is short. The current will rise quickly. Maybe it will reach the rated current of a secondary winding at maybe 5 or 10% of the rated voltage. So we have to take care of when we are getting open circuit, short circuit test, so that we can increase slowly. So once we obtain this measurement, open circuit, short circuit test, transformer rating can be obtained single phase, be rated by a rated, and for three phase we can multiply this magnitude of 3. So we can calculate a parameter for the transformer. For example, here, if we have this measurement, if we go this measurement for open circuit, the open circuit of 450, no load current of this magnitude, and a core loss of this, we can calculate the core components. So from that, calculate IC, a core loss current. A core loss current is obtained by using open circuits power divided by voltage. So this calculates this current magnitude of current is obtained. But the imaginary part of the current is obtained by using the measured current minus calculated current. So we can use this relation, I core square minus IC square is equal to this magnitude. And this is the magnitude of voltage current. We will obtain imaginary current of this. So the imaginary current, imaginary, is obtained as this current. So we have measured current of 1.2. We have calculated current of 1.3. I maximum. Okay, so I imaginary is equal to I open circuit minus I current. So I maximum is obtained by this. So finally, I imaginary is obtained from this relation. We have this magnitude. We have this magnitude of current. So this is the calculated current for. So from this, we can calculate a core resistance and core reactance. This will use I open circuit, then measure the total. Then core current, because it's active. So IC is obtained from this. I imaginary can be calculated by using this relation 1.24 square minus 1.6 square, which is this magnitude. So we can calculate a core reactance and the core resistance. Core resistance is obtained as BOP divided by a current. So this is a core resistance. Core reactance is obtained by BOP circuit divided by imaginary current. So this is the reactance part of current. So we give the reactance of the system or the transformer by using this equation. Again, from a short circuit test, when short circuits happen, what will be the parameter that can be determined? So during short circuits, the core parameter is taken as open circuit, because compared to the short circuit, as you have seen, the magnitude of the core resistance and the core reactance is high, so we can calculate a winding impedance. So from measurements obtained, this is a short circuit voltage magnitude applied. A short circuit voltage magnitude applied. This is a short circuit current measured, whereas the copper loss obtained is magnitude. So we can calculate the total impedance, equivalent impedance. We know the turn ratio, previously also determined this turn ratio. Calculate the Z impedance from equivalent impedance HC side. For example, Z equivalent of B short circuits divided by I short circuits is this magnitude, because it's calculated at high voltage side, because the low voltage side is shorted and high voltage side is given a supply of this magnitude. So this Z equals obtained at high voltage side. So we can calculate the R equivalent. R equivalent is obtained by dividing the power P short circuit by I short circuit. So this is the magnitude of core resistance, winding resistance. This is the total impedance. We can obtain the reactance of the winding by using this relation. This is the reactance of the winding. So, referred to the primary side, since the core parameters were obtained on the low side, the voltage side, we have to refer the resistance and impedance of the low side. So, we know that the current ratio is 26:151. So we can take the ratio of R equivalent divided by SK, Z equivalent. So we have this magnitude of impedance and resistance referred to the primary. So this is how we can represent a transformer mediator for a power flow analysis. We can obtain a simple circuit which is only voltage source, then series reactance, and terminal voltage for a transformer 2. Thank you for attending. If you have any comment, you can put on my YouTube channel.